Okay, so actually the next two lectures I'll talk about methods for finding algebraic solutions of linear differential equations. And I'll say from the start, there will be two methods. One is due to a sequence of people. Bit by bit, it was developed. Started with Camille Jordan, and then was improved by Painlevé and Boulanger, and finished off by Risch. So it's a decision procedure. It shows you that one can decide, but it's about as far from effective as one can get. And my next lecture, I'll talk about a method of Fuchs, who also had ideas about this. And it's it's not quite as terrible as the first method. So let me start with, I'm going to always be working over the algebraic closure of the rationals with x adjoined, and my derivative is d dx. And I'm going to start with a differential equation. For the AIs and here. And make things a little easier, I'm going to assume, since we're looking for algebraic solutions, I'm going to assume from the beginning that I have regular singular points and rational exponents. And that's a reasonable assumption. I'm going to make a slightly unreasonable assumption, which will make things a little easier. I'm also going to assume that L of y is irreducible, meaning that I can't write L as the composition of two operators of smaller order. One can decide this, but makes life simpler. And I will come back to this point. Where I use this is to say that if L of y has one non-zero algebraic solution, then all solutions are algebraic. And I'll say why later, but I'm going to use that. So this Jordan, Painlevé, Boulanger, Risch algorithm. So Boulanger was a student of Painlevé, seems like an interesting combination of words. It proceeds in two steps. The first step is to decide if L of y equals 0 as a solution y such that when you take the logarithmic derivative is algebraic. This step is really purely algebraic. And it's the algebraic heart of the algorithm. And this is as far as Jordan and Boulanger got. The next step was given U algebraic. When I say algebraic, it will always be over this field. Decide if there exists a Y, also algebraic, such that U is Y prime over Y. So there are two steps. So Jordan, as far as I can tell, is the first person to consider this first step. Is that okay? Then if I have such a Y, it will automatically be a solution. We'll say more about that. Okay, so the first step, Jordan approached this by first proving a group theoretical result. Excuse me? Yes, so independent of differential equations. I have an algebraic function. When is it the logarithmic derivative of an algebraic function? So Jordan showed, I think this was 1878. He said that there exists a function that just depends on n, such that if G is a subgroup of GLNC and it's finite, then there exists another subgroup. There exists a subgroup G, H of G. H is a normal subgroup, normal abelian subgroup of G, such that the index is bounded by J of n. So there's a function just of n, independent of the size of the group, so that if you're in GLN, your group has a normal abelian subgroup of this bounded index. And not sure that he gave an explicit form for J of n, but the proof, he used some recent results of CELO. The recent results are what we now know as the CELO theorems, which CELO published in 1872. So it was using the modern technology of the time. So this has been, it was Jordan, it was improved by Schröer, Speiser. People, there are lots of bounds, all of them are horrible. So for instance, we now have the best bounds. Recently, in the 21st century, n plus 1 factorial, as long as n is bigger than 71. So he used the classification of simple groups, and this is sharp. So the symmetric group on n plus 1 letters lives inside GLN, and this bound is for this group. Yes, so this appears in a paper talking about differential equations. We proved it precisely for this. So so on my exercise sheet, I have a bibliography, and I give the references to all of these people, so you can look at it. There's a non-constructive proof, a very nice short proof due to Terry Tao, and it appears in his blog, of course. So again, I give that reference in the bibliography. And the key fact about the proof is it's a finite group, so you can assume it's a group of I say not orthogonal, but unitary group. And so there's a measure. You can talk about size. And the key fact is if you have two elements, a certain distance from the identity, their commutator is closer to the identity. If you have a finite group, there's kind of a lower bound to how close you can get to the identity, and then all of a sudden things commute. And then this kind of an estimate comes from a volume estimate, using again the metric. So the thing I quote in the bibliography, it's a blog entry about many things. You have to look down, it's a short paragraph. You can see it. It's a very nice proof. So I'm not going to need the full strength of this group, of this theorem. I'm not going to need the fact that things are normal. So all I want is an abelian subgroup. And so I'm going to say A of n, this is the bound on the index of an abelian subgroup. I mean, there are lots of them. You take any element, generates an abelian subgroup. And of course, A of n is less than or equal to this. And I know some of the numbers. A of 2 is 12, A of 3. I mean, you'll quickly see why this becomes a little unmanageable. So it's not a pleasant number, but it can be. I'm going to use this. Okay. So J is for normal abelian subgroups. I'm saying I don't need it to be normal. I just need it to be abelian. No, I don't, but it's more than, so there is a copy of A4, of a central extension of A4 of order 120 inside of SL2. So it's large. So for small numbers, it's large. And for large numbers, it's also large. No, I don't. In fact, I will need something weaker than this. And I'll talk about that next time. So I don't even need abelian. I need something weaker. this just depends on the group. The weaker thing will depend on the representation a little more. Okay, so now let's see, what does this mean for Galois consequences? Okay, so we're going to start with a Picard-Bessio extension of little k. And I'm looking for algebraic solutions. I'm under the assumption that all solutions are algebraic. So K is going to be an algebraic extension of little k. We have the differential Galois group sitting inside of VLN, Q bar. Everything is over Q bar. And from the Galois theory, I know that the fixed field of G is K. Oh, by the way, G is going to be finite now. So I've been talking about the differential Galois group. It was automorphisms that also commute with the derivation. You could ask, well, are there automorphisms which don't commute with the derivation? And in fact, the answer is no. This, just by itself, implies that K is a usual Galois extension. And the usual Galois group is G. So this is just from elementary Galois theory. You have a finite group acting on a field. Let's live in the characteristic zero case and not worry about separability. You have a finite group acting on a field K. You look at its fixed field, then the field is automatically a Galois extension of the fixed field, and G is the Galois group. Yeah. So I'm going to see what consequences that we have, and I'll use those consequences then. Okay. Here. A basis of algebraic solutions. Okay. So what does abelian mean? Yes. So what does Jordan say? So I'm going to take H and G, or I should say weak Jordan. H and G, H abelian, and abelian, and the index is less than some bound. So the first thing we should know is that H is abelian and finite. It means we can diagonalize the elements of H. So you can put them all in Jordan normal form, but if it's an element of finite order, in Jordan normal form, it has to be diagonal. Okay. So these are Galois groups. They act on a basis. So there exists a basis of L of Y 0, I'm going to just say solutions of L, y1, yn, so that sigma of yi, it's a constant which depends on sigma and I, times yi. See? That's what diagonal means. So this is the first thing I'm going to use. Sigma in H. So now let's look at this haven't defined K, but K is always this Q bar of X. So we have this extension. Intermediate to it, there's the fixed field of H. So the Galois group of K over this is H, and over the big field, it's G. And Galois theory tells me that the index of K to H, it's the size of H. Index here, it's the size of G. And so we know that KH over K as a vector space has dimension equal to the size of this. It's because these indices, one is the product of the other two. By the way, if something looks wrong, it probably is wrong. So please stop me. So in particular, KH is algebraic over K of degree less than or equal to this. Okay, and now let's look at these y. If I look at yi prime over yi and apply sigma to it, sigma in H, this is C sigma I prime over sigma I. So this is yi prime over yi. So these have to be in KH. That's the Galois correspondence. So what do I have? I have that. Now I'm just going to take one solution. As I said, if I can just get one solution, then all solutions will be algebraic. So I'm going to just stop using subscripts. So the result of this is if L of y under the assumptions has all algebraic solutions, then there exists some, what am I going to call it? Z, L of z equals 0, and U, Z prime for C, algebraic of degree less than or equal to this A of n. So that's the conclusion from Jordan's theorem. Jordan was looking to classify actually the possible groups that can occur, and that's how he used this plus some kind of induction. He tried to classify the subgroups of SL2, SL3. He made some mistakes. Other people corrected it. They made some mistakes, corrections. It goes back and forth for a while. So what I'm saying is, if all solutions are algebraic, then the Galois group is finite. If I don't know all solutions, then it's not, and I'll come back to this later. Okay, so what do we want to do? I want to look for a possible minimum polynomial for U. Excuse me, say that again? I'm just, you know, yeah, it's one of these guys. I'm just tired of writing subscripts. That's all. Yeah, but linear combinations don't. So let's write down a possible is that okay? So I'm looking for this possible minimum polynomial, and I'm going to fix some m less than this number, this a of n, which we know a priori. And now, I mean, Jordan got this far. And now Painlevé and Boulanger, Painlevé, his article is a very quick, short article, I guess, in Comprendu. And Boulanger has an extensive memoir. I've, in the bibliography, I've pointed to the good parts, the pages where he does this. And it's incredible. There are two things that he does. First of all, he can bound the degree of Bm in terms of n and the exponents. And, well, I may do this later. In any case, it's an exercise. And the next thing he shows is that if the degree of Bm is less than or equal to r, then the degree of the any Bi is less than or equal to r plus m minus I. It's enough to bound this degree, and if either I'll do this here or in the exercise session. It really, it's a question of, if you know what Fuchs's relation is, it's a question of Fuchs's relation. Okay? The n and the exponents. N was the order. Yeah. So let me do this, because this is easy and fun. I don't need Jordan's theorem anymore. By the way, I was so happy to bring this eraser. Of course, somebody washed it last night and it's wet. So this is an example of no good deed goes unpunished. Okay. Yes? I'm sorry, I didn't hear you. I still can't hear you. Oh. Oh, where do I use that? So I don't. I mean, I'm only going to use the rational exponents that occur, but rather than you know, it just makes the I'd have to put more words into the argument. Let's put it that way. Yeah. So I mean, it's a harmless assumption. So why not make it? Okay, thanks. I haven't used it yet, but it comes. I need to know something about the exponents here. I need to know there's a bound on their size. I don't need to know the exponents. I just need to know a bound on their size. So let's see how we do this. So so this is going to be the minimum polynomial. So I want to prove 2. So the roots of p of u equals 0, I'm going to call them u1 to um. One root is of this form. The roots are it's irreducible. I'm assuming it's irreducible. The roots are permuted by the Galois group, and the Galois group preserves this kind of a relation. So the roots all have the form ui is zi prime over zi for elements that satisfy this. And I'm going to look at infinity. Now, I'm talking about algebraic functions as though they were functions. Well, I'm in some state of sin immediately. But think of these as Puiseux expansions. That's what I'm thinking of. Not as functions, but as these formal things. So what is the order of something like this? If I look at a point, expand it in the Puiseux expansion, take its derivative, divide by it, it's going to have order at least -1. So there'll be, at worst, there will be a simple pole. Okay? So the order, I mean, there may not be any pole, but the order at infinity of ui is bigger than or equal to -1. So there's this awful convention about talking about the order of poles and using positive integers. Not doing that. Okay, so let's look at B0 over Bn. This is plus or minus the product of the roots. Right? So its order at infinity is bigger than or equal to -m. The order of B1 over Bm. B1 over Bm is again, my convention is that plus or minus doesn't matter. And again, so its order at infinity is minus and minus 1. And I can go all the way down to Bm minus 1, Bi, Bm, the order infinity is bigger than minus n minus I. Okay. So that's one way of looking at the order of infinity. Another way is to just look at the order at infinity, Bi over Bm, order of, and I hope I have this right. These are polynomials. Right? I don't want to say this, I want to say degree. So let's put the two together. What do we mean by the... I have it backwards. Yeah, I think it's right. I mean, I looked at this again and again, so it's, you know, yeah, a convention, thank you. So I'm talking about the orders of poles are negative. My convention. Yeah, sure, but it doesn't make sense. So if this has large degree, right, compared to this, then at infinity you have a 0. As x goes to infinity, yeah, right, it's, anyway. Yeah, no, here it matters. So what do I have? Let's say that the degree of Bm is R. So I said less than or equal to R. Let's say it equals R. So I'm saying here that if we can bound the degree of Bm, then yeah. So what do we have? I have R minus the degree Bi bigger than or equal to minus n minus I. And when you do this, multiply by minus 1, you get R plus n minus I. Excuse me? Yeah. The other thing is also elementary, but you need to work a little harder. Okay? So, so what Painlevé and Boulanger did was they could bound the degree. So Jordan bounded n, Painlevé and Boulanger bounded these guys, the degree here, and then it's reduced to a question of elimination theory, which is again living in a state of sin. So what do we do? So let me take a little detour. So if I have u is z prime over z, L of z equals 0, u satisfies What's called the Riccati equation. I think we all know this, but let me at least say it explicitly. This is an equation of this form, Pn goes up to the n minus first derivative, an minus 1, A0, there's nothing here, and the p's are gotten recursively. Pi is gotten from pi minus 1. Via that recursion. This is the Riccati equation. Yes. Do I still have L? Yes, I do. So for example, if you have y double prime minus ay, then the Riccati equation is u prime plus u squared. Now I never know whether it's plus or minus. I think it's minus equals 0. And it furthermore has the property that r of u equals 0 if and only if equals e to the integral of u satisfies L of z. So solutions of the Riccati are logarithmic derivatives of solutions of the original equation. Yeah? Don't know. I mean, there are equations for ratios of solutions in the Schwarzian derivative, but yeah, you're kind of throwing away some information. I mean, in this case, the equation would be u equals a. So it's not quite so interesting, perhaps, for me. Yeah. So that's the Riccati equation. And what Henlevé and Boulanger suggest is the following. Yes. Right. Well, no, it's a fact. And then the way you derive the Riccati equation is you take y, look at y prime over y, and differentiate it a bunch of times. So what they suggest is the following. So let the coefficients of powers of x in a putative p of u, that is, we're looking for p of u, so we're going to say, well, I'm looking for it. I know what the degree is here. I know the degree here. So I write down a generic polynomial of the degree that I have found. But the coefficients are indeterminates. I don't know. This I chose this word because it's the same as in French. So putative is perhaps, yeah, or alleged. What is it? Okay. Sorry. So, can only please so many languages. So you have this, and then the statement dm u to the m plus d0 equals 0 implies r of u equals 0. This is equivalent to algebraic conditions on the coefficients. Sorry. This is P of U, right? What was your question? No verb. Indeterminants. Sorry. So zero, this is equivalent to polynomial conditions on these coefficients. On these coefficients of x. No, powers of x. So this, here's the u, but each b is a polynomial. And in those polynomials, I'm looking at the powers of x. Yes. Yeah, perhaps you need to sometimes say something is not 0 or something is 0, but okay. So, and well, one can decide whether or not they exist. You also want to say that it's irreducible, but all of these things have algebraic conditions. So that's it. That's the decision procedure for step 1. Okay. Yes. Yes. Yeah. An infinite. You get infinitely many solutions of the Riccati equation. No. I mean, you won't, but what should I say? There are statements about the Riccati equation. If you have too many solutions, then your original equation is of a certain form. But so the answer is I can't give a good answer. But it will give you an algebraic solution. Well, now you just, oh, I see what you're saying. Yeah, so no. So the Riccati, a solution of the Riccati equation is the logarithmic derivative of the solution of the original guide. I'm trying to determine if all solutions are algebraic. So no matter which one I pick, it better be algebraic. Okay? Okay. So part 2. I'm not going to prove 1 right now. So, sure, if you do, I do. Oh, I'm being assaulted.
I just wanted to say, I read your paper several times about this, and I presented this one once.
Yeah, but not like this.
Exactly,
yeah.
Exactly this.
Yeah, okay.
Exactly this. I got exactly this question.
Oh, thank you.
From Joseph Schicho, actually. We discussed afterwards, and the answer we came up with, I think, is the same.
I see. So it was a test.
I was really not sure, and I was happy that you.
Yeah. Okay.
So you just need to take one.
Yeah. Again, I'm assuming this is either irreducibility or some assumption that all solutions are algebraic.
Very, very nice.
Okay.
I really enjoying listening about this.
Well, it's a rerun for you.
Actually, actual author.
Well, yeah, anyway, thanks. Hi.
There is a paper on it.
Yeah, so, well, so the story is that I attended Dwork's lectures, and he lectured on this Dwork-Baldessari result. I don't know if you know this. This is about if you have a second-order linear differential equation with algebraic solutions, then it comes from a particular hypergeometric equation by some change of variables. Rational change of variables. And he started to look at third-order equations, to decide whether or not they have algebraic solutions. And, well, it motivated me to think about it. And I read this book of Schlesinger, this classical book, where the tools were there. So I gave this kind of elaborate proof, kind of theoretical proof that such a thing exists. And at the end, I discovered that Pallavet and Boulanger had done it. So
They did only for order 2 and 3.
well, yeah, but it's always the same with the classical things. They do it for specific cases, and more often than not, it works in general. So, it was known, the paper couldn't be published. Dwork gave a lecture at some conference that had a conference proceeding, and he said, well, why don't you put this paper in the conference proceeding? So it's a paper that appears in some conference proceeding in Canada. Okay, thank you. And it appears on my webpage. So we now have, we find numbers so that when I use those numbers as the coefficients, this equation implies this equation. I mean, something. So remember, these had indeterminate coefficients with x. So these are polynomials. This is some alpha. Little k, no, it's q bar of x, not. So the bar just goes over q. Okay. Okay. Yeah. Yeah. Yes. Yeah. And so anyone will then work. Okay, so I'm going to talk about step 2. I think there'll be a lecture on this next week, which I hope will be less naive than my talk. But so let me state this again. So step 2, well, I have it here. So given, you can forget about L now. Put it out of your mind. You have some algebraic function, and you want to know, is it the logarithmic derivative of an algebraic function? So the first thing to notice is that if I have y prime over y is in some field, better, f, and y is algebraic over f, then y to the n is in f. Now, n is it's a new version of n. It has nothing to do with the differential equation for some n. And positive integer. So that's something I showed in my first lecture. Many, many proofs. So what do I need to do? So to solve step 2, I need to know the following. Does there exist an n here and a y in this field? Say z in here. Let me not switch notation. Does there exist an n and a z such that z prime over z is mu? So here I wanted y prime over y to be u. Now I want this. And if so, then z to the 1 over m satisfies y prime over y equals u. So I found my y. I take the logarithmic derivative of this. It's 1 over m times the logarithmic derivative of that. And I found what I want, okay? So now, instead of looking for some algebraic function, I don't know where I want to look. I'm looking in here, but I now have to deal with some unknown integer. And I'm going to want to talk about residues. And so when you have algebraic functions, you know, there are lots of ways of parameterizing them, and residues kind of sketchy, not so good to do that. The correct way to do it is to talk about differential forms. Where the question of how you parameterize things is hidden. So this happens only if there exists a z and an m, so that dz over z equals mu dx. I'm going to call this omega. This is m omega. So this guy I know. I know what m is. I know what u is. I don't know m and I don't know z. So now there are various things I can say. What I'm going to say can all be stated in terms of valuation theory for this field. And you can talk about places and completions and orders and things like this. It can all be done just field theoretically. It helps psychologically to associate this is a function field in one variable, with a curve. That is, this should be the functions on a curve. So I'm going to let x be some non-singular model of this field. And this can be constructed. I can write down equations for this. Doesn't necessarily live in P2, but we have equations. Keep this in the back of your head. And I'm going to let I'm going to take a point P now is a point of X. And I'm going to let N sub P be the residue of omega at P. And that's some number. Now, if it's not rational, I'm in trouble because I want it to be coming from here. This z to the m, the logarithmic derivative of this is going to be some rational number. So I can assume that it's rational. Okay. And as a technical point, I can actually assume that it's an integer. That NP is an integer, and I don't want to check this at home. You can replace omega by some power which clears the denominators, some multiple. And if I can do everything for this, I can do it for the original thing. Take my word for it, okay? Yeah, exactly. Yeah. Okay, so it's a this Penlevé Boulanger thing is really nice. You should look at the original paper. Anyway, here we are. And so what am I going to do? I'm going to look at a divisor. Okay, so this is a divisor on X. I write my divisors additively. And what I want to do is decide if there exists some m, positive integer, such that when I multiply, this is precisely the divisor of a function. Okay. I want to know whether it's a principal divisor. That is, so the divisor of a function is you write down where it's poles and zeros times their multiplicity. And if so, find the smallest m. Yes. I started with this guy, so I have u dx. U is given. So I can write down the divisor of this. And not the divisor, but I do it this way. For sum. Okay, is that better? Okay. And B, if this is the case, for this M and F, decide if F prime over F is MU. So I claim that's all I need to do. So the answer is no here, I stop. The answer is yes, I produce f for this m. I mean, any two such f's will differ by a constant multiple, so that it doesn't affect this, but I still have to decide this. So, I mean, I have an element in here, I have u in here, I should be able to decide whether this. Now, I have to convince you why this is enough, but first, it's understandable. So, why is this enough? Well, if there exists an m and a z such that z prime over z equals mu, that is, that's what I want to decide. Does there exist such that this happens? Then that z will be my f, and it will satisfy this. So if this happens, this will be satisfied. Perhaps not for the smallest, but for some m. The question now is, if there exists an m, why would the smallest m work? It might work for 12, but not for 6, you know. But in fact, it's again this business of you can just take powers. So the set of such m, this is some principal ideal. So there is a smallest one. Anything else is divisible by m tilde. So if I find some m that works, so if some m works, meaning for that m I get this, I can write m equals L tilde. M tilde times d is some z tilde. And you can, I'm going to let you do the computation yourself. You'll get that m tilde u equals z tilde prime z tilde. So if it works for some z, so mu equals z prime over z, and I'm not going to do the computation here because we'll do it wrong. No, but it is, but if I write it, it'll be wrong. Okay. So I'm going to deal with this. And now I need to use something serious. So I need to decide if some multiple of a divisor is principal. So, you know, we have criteria for when divisors are principal. There's the Abel-Jacobi theorem, which is an analytic criteria. which says if you think of the divisor as a zero chain, and you start integrating holomorphic forms along generators of your homology, and if those 2G numbers lie in a certain lattice, then the divisor is principal. The Jacobi theorem says. I don't know if anybody's ever tried to implement that numerically, whether you can make estimates that would make it work. It's kind of, did you happen to know if, no, okay. Anyway, that's not what I am going to do. So first notice that this non-singular model is defined over some K0, which is a finite algebraic extension of Q, a number field. Okay. We have a curve defined over a number field. There's a geometric object one can construct from this, the Jacobian, which is it equals the divisors of degree 0, that is, things of the form Ni, Pi, the sum is 0, where this ranges over all points in the curve, but the sum is finitely supported, divided by modulo divisors of functions f, principal divisors. Field. And one can construct this algebraically. You take the G products of the curve and you mod out by the action of the symmetric group, and you have to put an algebraic structure on that. You have the equations for X, you can get the equations for this Jacobian. And so what am I looking at? This has the structure of a group, right? You can add these things. And what I'm asking for is if I have some divisor in here, I'm asking, does there exist an M such that MD is 0? Is it a torsion element? That's what I'm asking. So we're defined over an algebraic extension of Q, this Jacobian. I'm going to take a big enough extension that contains the coordinates of the points that I'm interested in, the coefficients of whatever equations I've written down, but it's still some finite extension. And we know that in that case, Mordell-Weil theorem says this is a finitely generated group. In particular, the torsion subgroup is finite. So the torsion subgroup is finite. And I'd like to get a bound on this side. Now I'm going to quote some other things. So one can reduce things modulo a prime. That is, if I take a prime in this field, algebraic extension of Q. So I want to select, in fact, 2 primes. primes in K0, such that if I reduce the equations, these are good reductions. What do I mean by good reduction? I want the curves modulo those primes to still be non-singular. Yeah. Excuse me, it's an ideal. And they sit over actual primes. So they're real prime numbers living in them. Okay. So if I do that, there's a theorem that says I can do the same thing for the Jacobian. If J is Jacobian of X, say J1 is, I can reduce this. J2 is the reduction E2. Okay. And furthermore, I get a map homomorphism me say it correctly. Homomorphism, which is an isomorphism on divisors of order prime to pi. So something can happen to divisors whose order is divisible by these actual primes living here, but for the others, it's okay. Now the thing to note is I have residue fields. Of course, these things are defined over the residue fields, and these are finite fields, so these reduced Jacobians are finite. And you have the equations, you can figure out all the points in that reduced field. And in particular, you can bound the size of these JIs on, I don't know, I'm running out of notation, these residue fields. The finite fields, you have a bunch of equations, you can count the number of points. You don't have to count them, somebody's counted them for you. I think they gave a bound plus q to the 2g, where g is the genus of the curve. This is bound. Yeah? Maybe I am too. Yeah? Yes. Yeah, I said I want to pick it large enough so that it contains whatever numbers I need. Okay? Yes? Yeah, you do. Well, I'm given the points. So I start with the divisor. I've picked the points in Q bar. So I adjoin the coordinates of those points. What more do I need? Yeah, right. So I'm looking for I see what you're saying is, yeah. No, I guess I don't see why you might need new points. We can discuss that. Well, what computation would you need to do that might require new points? Let's talk about this later. Okay. So now Q is the size of the residue field. So perhaps QI. QI is the size of the residue field. I think, in fact, there's a general bound on the number of points in an abelian variety. But in any case, just count. Don't believe they. G is the genus of the curve. Yes, it is. I'm looking at the points of this reduced Jacobian. So I've now defined this over a finite field, and I'm looking at the points in the finite field. Yeah. And now I need two primes because of the following. So let's say that, so if D has order P1 to the N1, P2 to the N2, M, where M is relatively prime to P1 and P2. If I reduce in P1, I said I get a homomorphism. So the order is going to be, I don't know what's going to happen with P1, but it'll have order at most N1. I preserve this. This is still okay. Do it for D2, P1 to the N1, P2 to the N2 bar M. Each of these numbers is bounded, so I can calculate N1 and N2 and M. So if I know those two, one person is shaking their head yes, that's a hopeful sign. By the fact that I can't preserve things that happen to involve a prime when I reduce mod P means I have to do two primes. So I can bound this number and bound this number. So in fact, I can calculate these things. So that's it. We're done. I have a bound on the order. I said that's all that I needed to do. I've erased that fact. I found some numbers, so I can find the smallest number. And what I need to do is I have a bound. So from this bound, so I can bound M, and I need to do two things for J equals 1 to M. I need to decide if JD is principal. So there are effective versions of the Riemann-Roch theorem. You can, classically, they knew how to decide this kind of a question. There are more recent things. Again, do you happen to know if this kind of thing is implemented? There's a paper by Hess in the last 10 years that gives a nice algorithm for this. You can decide this, and then you just continue. We found this, and now you have to decide this, and you're done. So that's it. That's a decision procedure. There's a lot involved, but the two things that I want to point out is that the first step really is just algebraic manipulations. And the second step is arithmetic. They're arithmetic questions enter. And so I'll ask this question. I've asked it many times. There's this Grothendieck-Katz conjecture that if you have rational solutions mod p for enough p, then you get an algebraic solution. And the question I have, is there a reasonable conjecture about the Riccati equation? I mean, I'm not sure what the conjecture would be, but what happens to the Riccati equation mod p? Or you have enough solutions for the Riccati equation mod p, what does that say? Because we'll see that this question, the Grothendieck-Katz question for first order equations, is solved, but it's solved through arithmetic, right? It's equivalent to a statement about Galois groups. And the solution involves arithmetic. There's no question about that. And I'm asking very naive questions. That is the obstruction, where is the arithmetic obstruction to the Grothendieck-Katz conjecture? I'm not saying this solves it or anything, but I'm just curious what people know. Somebody knows something, they should tell me. Anyway, this is this. Stop here. Next time, I'll give another algorithm. It's really more a method that tries to produce an equation for y directly. And I say it's not an algorithm because you have to a priori know the group, and you have to know invariance of the group. And it's a method proposed by Fuchs. And although these methods, I mean, they're not effective, but they reveal interesting ideas. I feel that's the content of them. I mean, people may complain, let's say, point out to me that these are not effective, but the ideas behind them are interesting. I hope you enjoyed it. Well, thanks.